So we've met our 4 gas laws so far. So we've met Boyle's law, which says pressure is inversely proportional to volume. We've met Charles's law that says volume is proportional to temperature. We've met Gay-Lussac's law that says pressure is proportional to temperature. And we've met Avogadro's law that says volume is proportional to number of moles. And the nice thing about all these individual gas laws is that they're quite easy to use. The bad thing is there's 4 different ones, which is kind of a pain. But we can probably deduce that there will be some mathematical relationship between P and V and N and T. And we can actually bind all these laws together to get what we call the ideal gas law. And the ideal gas law basically says pressure times volume is related to the number of moles in the temperature. We just need a constant, a proportionality constant, which we normally give the symbol R to. And R we normally call the ideal gas constant, or sometimes the perfect gas constant. And R takes values depending on your units for pressure and volume and temperature. But in this course here, we'll often find R is 0.0821, and it has units of atmosphere liters over moles times by Kelvin. So it has those weird units there. And you can see if you take the equation above and you rearrange for R, R is equal to PV over NT. And so R just has to have the units of pressure times volume, so atmospheres in liters, let's say, and chemical amount in temperature, so moles in Kelvin. So that's why R has those weird units. So let's go ahead and go to Mars, shall we? So one way to go to Mars, it turns out getting to Mars is kind of hard, but one way to go to Mars is to basically send something inside a giant balloon. And we can send something inside a giant balloon, maybe of helium gas, and basically it will just hit the surface and it will bounce, and eventually it will quit bouncing, and then we'll let out the helium, and we can let out a little rover, and it can run around on the surface of Mars. So we've tried parachutes before, and it turns out that parachutes are kind of hard because Mars has a very thin atmosphere. So let's go ahead and calculate. Maybe we need to know what volume in order to have, say, 100 liters of helium on Mars. And it turns out if we measure the temperature of Mars, it's rather cool. Let's say it's a rather cool 7 degrees C today. The pressure on Mars is kind of low, actually. Maybe it's 0.020 atmospheres, maybe. And we need to know how many grams, how many grams of helium. And the nice thing about helium, right, is it's very light, very low atomic weight, do we need in order to have a balloon that's 100 liters big. So we can take our ideal gas equation, PV equals nRT, and we can ask ourselves, what do we know here? We're told the pressure on Mars, right? So the pressure is 0.02 atmospheres. We're told the volume of the balloon we need, that's 100 liters. We've looked up the gas constant on the last slide. We're told the temperature, although we got to be a little bit careful because the temperature is 7 degrees C, but if we add 273 to it, we get the temperature in Kelvin, so that's 280 Kelvin. So we've got T, and oh golly gosh, right, we need to know N, the number of moles, according to our ideal gas law equation, but in our problem, right, we have the number of grams. So we can certainly find the number of moles, and we can find the number of moles by dividing both sides by RT. So that gives us N, and let's see, if we divide by RT, the R's and the T's go. So that tells us that N is equal to P times V over R times T. And well, let's go ahead and find the number of moles, and then we'll see how that's related to grams here in a second. So we can go ahead and plug in. So the pressure is 0.020 atmospheres. The volume we wanted was 100 liters, so that's a big balloon. Our gas constant is 0.0821, and then we've got those funky units of atmosphere liter over mole Kelvin. And we got our temperature of 280 Kelvin. So we can play the unit cancellation game. So the atmospheres cancel, so do the liters, and the Kelvin cancel. And we're left, if you like, with 1 over moles. And if you take 1 over something and then you take 1 over it a second time, you're back to where you started. So that will give us the number of moles. And we can go ahead and run this in on our calculator. And on your calculator, be super careful here because you're dividing by 2 things multiplied together. So if you go ahead and you take that number, 0.02, and multiply by 100, and then divide by 0.0821 times by 280, you actually get the wrong answer because your calculator takes these two, multiplies them together like it should, divides by this one, and then if you times by 280, it takes the whole result times 280, but you want to divide by 280. So I'd recommend using parentheses here, so don't be caught out. And check along, make sure your calculator agrees, but I get quite a small 0.0, so nothing significant yet, 87 moles. And what was it? It was moles of helium. Now, that wasn't the question, was it? So the question was not how many moles of helium, right? It was how many grams of helium. So how do we change moles into grams? Well, actually, this is kind of fun. So we can look at our periodic table. We can find helium. Helium's got two numbers, one above and one below. The number above, if you remember, is the atomic number. And so the atomic number Z, that's the number of protons, which is also equal to the number of electrons in the atom. And underneath, it's got the atomic mass. And the atomic mass of helium is, depending on your periodic table, it might have a few more digits, but mine says it's 4.00. So we can use that as a conversion factor, right? We can say 1 mole of helium, if you excuse my writing, weighs 4.00 grams of helium. Its molar mass is 4 grams per mole. So we can set that up now, right? So our last part of the problem is changing moles into grams, so 0.087 moles of helium, and we can multiply by our factor. So we want the grams on the top, and the moles that need to cancel go to the bottom. And we can go ahead and we can just cancel those out. So moles of helium cancel. And so, so we can just type that in on our calculator. And to two significant figures, I get that to be 0.35 grams of helium. So hardly any helium at all would blow up to a giant 100-liter size balloon on Mars. So pretty awesome.